Now let's talk about another kind of function that's going to be important to us, the cumulative distribution function, which I'll call a CDF. So this is much like the cumulative stuff that we did with frequency tables, which is realistically exactly why that was there. The cumulative probability or the cumulative distribution function is really telling us the probability of getting a certain value or less, right? That was the cumulative idea that we had before. Realistically, this works exactly the same as our cumulative relative frequencies, our cumulative percentages that we were using in Minitab before, where it's going to give us, instead of the percentage that are this value or less, it's going to be the probability of getting a value that's this or less. So let's talk about how that actually works, because I think once we make the table, you'll see that it works just like the other one. Now there's just a bit of notation that I should have talked about in the last video, so let me just get to it now. I've written this really funny construction here, right? Hopefully we recognize the probability of part of it, but I wrote that y equals y. That seems really weird, and it took me a long time to really wrap my head around it when I was first doing this probability stuff. The key here is really that we've got an uppercase and a lowercase. I know that doesn't seem like much, but this capital Y is a random variable. It has no value, right? Until we actually do an experiment and gather data. And then we'll have an actual observation, lowercase y. Well, notice I've listed my observations here as lowercase y's. Like, so this is, I've got some random variable that's 0 through 5 here, and 0 is one possible outcome, and its probability of occurring is 0.01. So what this number, let's say right here, is the probability that our random variable y equals 1, right? So this little y right here is this column, right? So it's the probability right here is the probability that our variable equals 4. Okay? So this is really what we're getting at. I realize this probability that y equals y is awkward, but it really is just compact notation for something that we're going to use a lot. Okay. So what I've given here is a PMF that I stole out of a textbook. It said the variable was the number of times that a newborn baby wakes up their parents at night. So we could tell, obviously, this is fake garbage data, because if you've ever had a newborn in your house, you can definitely be awakened way more than 5 times a night. Easily, right? But anyway, and the probability of getting awakened 0 times is 0, right? That's not even 0.01. But anyway, let's make sure this is an actual PMF table. So what do we have to have? There's got to be a probability listed for every possible value of my variable. Okay, well, yeah, there's a probability listed. Second, all those probabilities have to be between 0 and 1. That's true as well. And the last thing I need to check is that these add up to 1. Well, I won't pull up my calculator here, but I can tell you that yes, they do indeed add up to 1. So this is a PMF table, just having my possible outcomes and then the probability that that outcome occurs for my random variable. And now I'm going to make the cumulative distribution function, which would be the values for the probabilities of observing. For example, right here will be the probability of being awakened 4 times or less. Okay, so let's look at how we can construct this. Well, just like those cumulative relative frequencies in a frequency table, there is nothing lower than this first one, so I can just copy that over. Right. Can't be awakened less than 0 times in a night. And then to get this next number, it's just this plus this. And it gets me 0.16. There's a 0.16 chance of me being awakened 1 or less times per night. Now this, and this will give us this answer, which is 0.37. And of course I can just, like I had a trick before, instead of adding this, and this together, this number was already these things, so I could just add this and this to get this number. So 0.37 plus 0.33 gets me 0.70. This plus this gets me 0.88. And the last number is always 1, just like we had with the cumulative relative frequencies. What does that mean? There's a 100% chance that it's going to, whatever happens will be a possible value. Right? Whatever happens, it's going to be the highest number or a lower number, right? The highest possible number or a lower one. Well, yeah, of course, that's always going to be true. So that's how I make a cumulative distribution function from a probability mass function. So just to make sure we're actually following what this table is actually telling us, let me try to answer a few questions from it. All right, so what's the probability of being awakened 3 times? All right. Well, we mean 3 times exactly, right? Of being awakened 3 times. So let's find 3. That would be my outcome. And we're not saying 3 times or less. We're saying 3 times. So that's 0.33. That's the probability of being awakened 3 times. Now, the probability of being awakened at most 3 times. All right. So at most means it could be 0 or 1 or 2 or 3 at most, right? That's the highest it could possibly be. So that's 3 or less. At most 3 means 3 or less. Well, that's the cumulative stuff. Whenever we think of or less, we should be thinking of cumulative stuff. So 3 or less is this one. So there's a 0.7 probability of being awakened 3 times or less. What's the probability of being awakened more than 3 times? Well, this is just like those frequency tables where I can answer less than questions directly out of the table, but more than questions, I got to add stuff up, the individual probabilities. So it said more than 3 times. So more than 3 times would either be 4 or 5, according to this table. As I said, if you become a parent, you'll find out it can be way more than that. But anyway, 4 or 5. So I need to add up these 2 probabilities. The probability of being awakened 4 times is 0.18. The probability of being awakened 5 times is 0.12. When I add these together, I get a 0.3 probability of being awakened more than 3 times, right? That'd be 4 or 5. I hope you're seeing that this really does work just like our frequency tables, which was really just a precursor to this. And last, what's the probability of being awakened at least once? All right, at least once. Well, at least once would mean 1, 2, 3, 4, or 5 times. This is going to be tedious for me to calculate. I don't love doing tedious things. So let me just tell you, whenever you see at least once, I want you to think of a trick. Because this comes up all the time, like in real life. This happens a lot. So at least 1. What's the complement of at least 1? Less than 1. Specifically, when I'm counting, less than 1 means 0, right? 0. So instead of adding all this stuff up, I'm going to use a trick which says the probability of at least 1 is 1 minus, right? That was our complement rule from the classical probability unit. 1 minus the probability of the complement. And the complement of at least 1 is 0, right? So that's the probability that y is 0. So what was that one? 0.01? And that gets me 0.99. Right? So yeah, I wrote it all out, and it took me a little bit to explain here. But it's really just 1 minus the probability for getting 0. So 1 minus 0.01 gets me 0.99. To me, that's a lot faster, especially when, for example, I have a table of 20 things. That's going to be tedious, and I'll probably skip a number in my calculator or something. So use that trick whenever you see at least 1. Think of the complement and do 1 minus the probability of getting 0 instead of directly finding the probability of at least 1. All right, so that's how I make a CDF, cumulative distribution function table, from a PMF, probability mass function table, and how we use these. Again, if you followed what was going on with frequency tables, especially with those relative frequencies, this works almost exactly the same.